Earlier we were talking of two noded, that is linear elements, and for two noded elements our element, since we are talking of one dimensional element, had a uniform area of cross section, and the two nodes were the two extremes, they are nodes 1 and 2, and then we defined a local coordinate system given by zeta. We said zeta will be minus 1 here and zeta will be plus 1 over here. Okay. Similarly, we decided that if the deformation here is q1, the deformation here is q2, then u, which is a deformation at any arbitrary point here, will be given by n1 q1 plus n2 q2, or it will be given by n times q, okay, where n and q are matrices. This is what we had for the two noded element. When we talk of quadratic shape, functions between 2 points, it is not possible to define a unique quadratic curve. Okay, so we will need a three noded element. If you remember, the shape function in this case were linear shape functions which looked like this. Okay, this is point 1 and this is point 2, and if I draw n1, that looked something like this, and let us say n2 will be like this. Okay, this is n2 and this is n1. Okay, we said n1 will be 1 at node 1 and 0 at node 2, and n2 will be 1 at node 2 and 0 at node 1, where n1 and n2 are the shape functions which are basically the weightages we are assigning to q1 and q2 to find out the deformation at any arbitrary point within the element. Now what we will do is that instead of since we are talking of quadratic shape functions, we cannot define a quadratic curve between 2 points. So now we will have a three noded element which looks something like this. One node is at one end, the second node is as usual at this end, and the third node will take somewhere in the center. Okay, so now we have three nodes. The deformation, the positions are x1, x2 and x3, and the deformations will be q1, q2 and q3. Okay, and again if I want to find out u at any arbitrary point, that u will be a function of q1, q2 and q3, but now we will do a quadratic interpolation instead of doing a linear interpolation. Okay, and we will again define a local coordinate system which will be, let us say, zeta, and zeta at this point is minus 1, zeta here will be 0 and zeta here will be equal to 1. Again we define Lagrange polynomial. We have something similar to that. Okay, so we will define a local coordinate system given by this description, and we will define u to be equal to n1 q1 plus n2 q2 plus n3 q3, where n1, n2 and n3 are the shape functions associated with the 3 points 1, 2 and 3. Okay, and the way we will take these shape functions, this is my point node 1, node 2, and let us say this is my node 3. n1 is a weightage associated with the point 1. So our criteria that we will choose will be that n1 will be 1 at this point and will be 0 at both the other points. Only then this will be a valid statement. Okay, but if n1 is 1 and n2 and n3 are 0, u at point 1 will be equal to q1, and that is what we want. Okay, so the curve in this case would look something like this, as it is 1 here, 0 here and 0 here. Okay, and it is a quadratic curve, so it would look something like this. Similarly, if I talk of n2, this is n1. If I talk of n2, it has to be 1 here and 0 at both these points. It will be symmetrical to this curve. it will look something like this. And this is N2. Okay, and N3 it has to be 1 here and 0 at both these locations. So N3 would look something like this. Okay, and since at this point we have zeta equal to -1, zeta equal to 0 and zeta equal to 1, we will define N1, N2 and N3 in terms of these zeta. Okay, and again N1 is 1 at this point and 0 at both the other points, and it is a quadratic function. Okay, so N1 would have a term of zeta and 1 minus zeta in it. Okay, if it is zeta into 1 minus zeta multiplied by, let's say, some constant c, okay, then at zeta equal to 0 this whole term will be 0, at zeta equal to 1 also this whole term will be 0. Okay, so we will say N1 will be equal to this. Okay, c is a constant and this gives us a quadratic function for N1. Okay, and then we know that N1 at node 1 is equal to 1. Okay, at node 1 zeta is equal to -1, so we can put that value over here. We will get N1 which is equal to 1 will be 1 into this will be -1 into 1 minus -1, which is 2 into c. So you will get c to be equal to -12. Okay. So this way we will get N1. If you look at this expression, you will get N1 to be equal to -12 into zeta into 1 minus zeta. Okay, this will ensure that this N1 is a quadratic function of this shape. It is equal to 1 at this point, 0 at this point and 0 at this point. Okay. Similarly, if we look at N2, we will say N2 will have some constant c, let us say C2, multiplied by zeta and multiplied by 1 plus zeta. Okay, that is because at zeta equal to -1 it has to be 0 and at zeta equal to 0 it has to be 0. So we will have these two terms, zeta and 1 plus zeta in it. Okay, and again we will have at zeta equal to 1 N2 is equal to 1. If I put this back over here, I will get C2 to be equal to half, or we will get N2 to be equal to half of zeta into 1 plus zeta.
Excuse me?
Yeah.
The purpose of naming the nodes in the linear element as 1, 3, 2 should have been 1, 2, 3 because in while assembling, so it will be better when 3 or 4 will get coupled up.
No, that doesn't happen that way. Well, what will happen is this is 1, this is 2, right? From the next element you will get this will be the first node of that. This will be the first node of that. The second node will be at that end. Okay, so the second location as it is, you will see that the stiffness matrix of this will be larger. It won't be a 2 by 2 matrix. It will be a 3 by 3 matrix.
3 by 3.
Okay, so when you assemble a 3 by 3 matrix, you will see that this numbering will be more convenient. We will see that in the end. Okay, because if I give 1, 2 and 3, I mean strictly speaking you can always do that. Okay, but this numbering will be more convenient as far as assembling the matrix is concerned. Okay. Now we have got N1 and N2. Similarly, if you look at N3, N3 will be some constant C3 multiplied by 1 minus zeta into 1 plus zeta. Okay, and at zeta equal to 0, N3 is equal to 1. Okay, at zeta equal to 0 it is 1, and both these endpoints it has to be 0. So we will have a term of 1 plus zeta and 1 minus zeta in it. Okay, if we put this, we will get C3 will be equal to 1. Okay, therefore N3 is equal to 1 minus zeta into 1 plus zeta. Okay, so the three shape functions we will have, there will be this, then this and this. Okay, and we've mentioned u is equal to n1 q1 plus n2 q2 plus n3 q3. Okay, which we will write that as n times q, where q is equal to q1 q2 q3 transpose, which is the element displacement vector. N is n1 n2 n3, which is a set of shape functions. Okay, any questions up to this point? Okay, and the next thing is in one dimensional elements, the strain epsilon, this is given by du by dx. Okay, so du by dx, if we take up this expression, it will be d by dx of n1 q1 plus d by dx of n2 q2 plus d by dx of n3 q3. Okay, of these q1, q2 and q3 are constants. Okay, and n1, n2 and n3, they are functions of zeta, and zeta in turn depends on x. Okay, so if you look up this formulation, we found out expressions for n1, n2 and n3. This is n3 in terms of zeta. Okay, and zeta in terms of x. Okay, zeta in terms of x is given by, zeta will be equal to 2 times x minus x3 divided by x2 minus x1. Okay, so if you use this, we can evaluate this derivative. If you notice, the steps that we are going to follow will be the same as the steps we had for the two noded element. Okay, the first two noded element that we have taken, linear elements, there also we defined u equal to nq. From that we found out epsilon. Once we found out epsilon, that we got epsilon to be equal to b times q. Here b is nothing but the derivative of n. Okay, once we got epsilon, then we put that in the potential energy expression and got expressions for the stiffness matrix and the force matrices. Okay, we are going to follow exactly the same sequence in this case also. Okay, so if we carry out this differentiation, derivative of n1 with respect to x will be nothing but derivative of n1 with respect to zeta multiplied by derivative of zeta with respect to x multiplied by q1 and so on. Okay, so again derivative of zeta with respect to x will be there in all the three terms. So what we need is a derivative of n1, n2 and n3 with respect to zeta. Okay, that we can get from our definitions of n1, n2 and n3 from these terms. Okay, so here, so derivative of n1 with respect to zeta, that will give us, this will be minus half plus zeta, so it will be plus zeta, okay, which is zeta minus half. Is that right? 2 zeta minus 1 by 2. Yeah. n2, this will give us half plus 2 half plus zeta. Okay, and this d of n3 with respect to zeta, this will give us minus 2 zeta. Okay, so these are the three derivatives which we will have, and we put them in this expression. So what we will get will be from this we will get epsilon to be, let me write it in again in a matrix notation. Multiplied by q and of course multiplied by d zeta by dx. Okay, dn1 by d zeta will take from there will be 2 zeta minus 1 by 2. dn2 by d zeta is 2 zeta plus 1 by 2, and dn3 will be minus 2 zeta, just multiplied by q, and d zeta by dx will come out to be 2 divided by x2 minus x1. Okay, so this again we will write that this will be equal to b times q, where b is this matrix multiplied by this constant. Okay, x2 minus x1 is nothing but the length of the element. Okay, so this will be nothing but 2 divided by LE. So we will get b will be equal to 2 divided by LE multiplied by 2 zeta minus 1 by 2, 2 zeta plus 1 by 2 and minus 2 zeta. Okay. Any questions up to this point? If you notice, in this case the strain epsilon will be varying within the element because it depends on zeta. Okay, zeta is basically the, if this is my element, zeta is changing along the length of the element. Okay, at this point zeta is minus 1, here it is 0 and here it is 1. Okay, so this strain is going to vary within this element and will vary as a linear combination of q1, q2 and q3. Okay, the linear combination of the three parameters here. While in the previous case when we were taking linear shape functions, the strain within the element was constant. Okay, so those are the constant strain elements. In this case the strain is not constant but is going to vary linearly. Okay, as a linear combination of these three. Okay, then once we have an expression for epsilon, we can immediately get the expression for sigma, which is nothing but E times B times Q. Okay, where sigma is the stress, which is Young's modulus multiplied by the strain. Okay. Now let's look at the expressions for the potential energy. we will carry the same steps again. Potential energy is given by summation over all the elements of half integral of sigma transpose epsilon dV minus summation over all the elements of integral the u transpose f dV, again volume integrals, okay, minus summation over all the elements of integral u transpose t dA, okay, minus summation of qi pi. Okay. So, let us look at the first term, this term which is the strain energy term. Okay. So, we get strain energy of the element is equal to half integral of sigma transpose epsilon dV. Again we are talking of one dimensional elements, so replace this by A dx, okay, A into dx. So, within the element area is going to be constant, okay. So, this will be equal to half of A sigma is equal to E times B times Q, okay. So, sigma transpose will be equal to Q transpose B transpose multiplied by E. Okay, E is of course a constant, it is not a matrix. Okay, so E can come out. So, this will, I will take E out, integral of Q transpose B transpose, okay, multiplied by epsilon, where epsilon is equal to B times Q. Okay, so for instead of epsilon I will put B times Q, okay, multiplied by dx. Okay, and earlier also we have used the fact that dx by d zeta is going to be equal to LE by 2, okay, because my B matrix is in terms of zeta. So, I prefer to do the integration with respect to zeta rather than with respect to x, okay, and that I can convert by using this relationship, okay. So, dx is equal to d zeta into LE by 2, I can put that over here. Q transpose is of course a constant, okay. So, I will get this to be equal to half of A E Q transpose, LE by 2 is again a constant, so I will get LE by 2, okay, into integral of B transpose into B into d zeta, and this whole thing is multiplied by Q. Okay, let me just draw a line. Okay. Now, B is the matrix which is given over here. This is my matrix B. If I do a B transpose into B, okay, B is a row matrix of size 3. Okay, so if I do a B transpose, it will be a column matrix of size 3, and that is being multiplied by B. The product of the two will be a 3 by 3 matrix. Okay, a 3 by 3 matrix consisting of terms in zeta. Okay, and zeta is changing from -1 to 1. Okay, so I can carry out this integral, okay, because it only has terms in zeta, nothing beyond that. I can expand this integral and evaluate it. Okay, what we will get, or rather what we will do now, this step will say is equal to half of Q transpose into we will have terms inside which will contain E into A into LE by 2 into integral of B transpose B d zeta, and this whole is multiplied by Q. Okay, this will say is equal to half of Q transpose KE into Q. Okay, where KE is the element stiffness matrix. KE is called the element stiffness matrix. Okay, and if we carry out this integral, we will get KE to be given by okay, so KE will be given by this matrix, and the strain energy in the element is given by this expression. Is that okay? Any questions up to this point? Okay, then we will now take up the next term in the potential energy expression, that is a term of these body forces. Okay, if you want to evaluate this integral, this is integral of U transpose F dV. Okay, this is nothing but integral of U transpose F A dx. Okay, this will again be U transpose is n times Q. Okay, so this will be integral of Q transpose n transpose F A dx. Again I will convert that into terms of d zeta, so I will get this to be LE by 2 times d zeta. Okay, of these F is a constant, A is a constant, length is a constant. All these terms I will take them out, and of course Q transpose is also a constant. Okay, so if I take these terms out, I will get this will be equal to F A LE by 2 into Q transpose into integral of n transpose d zeta. Okay, this I will write that as F A LE by 2 into Q transpose into, this will be integral of n1 d zeta, integral of n2 d zeta, and integral of n3 d zeta. Okay, and again we can carry out the same integrals, and this whole expression, okay, we will find that this will be equal to okay, this whole expression will be equal to, now F into A into LE. F is the unit body force acting on the element, okay, force per unit volume. A into LE is the volume of the element. Okay, so this thing will come out to be equal to Q transpose multiplied by this term, that is F into A into LE, and then inside we get three terms which will be 1 by 6, 1 by 6 and 2 by 3. Okay. Now this is the total body force acting on the element, and this gives the proportion in which this force is effectively divided into the three nodes. We have three nodes. This is 1, this is 2 and this is 3. Okay. So what we can say is effectively 1/6 of the body force is acting here, 1/6 is acting here and 2/3 is acting over here. Okay, well, the total body force acting is this, which is divided in this ratio at the three nodes. Okay, and this will say this will be your Q transpose multiplied by, let's say, the body force vector for the element. Okay, so total body forces acting on the element are divided into the three nodes in this proportion. Okay, in a earlier case, when you are taking a linear element, we had two nodes, one here and one at the other end, and the total body force was divided equally in the two nodes. Now it is divided in the ratio of 1:1:2. Okay, or rather 1:1:4. Okay, 1/6 is acting here, 1/6 is acting here, 2/3 is acting here. Okay, this is as far as the body forces are concerned. Similarly, if you consider tractive forces, the term for the tractive forces that we have is integral of U transpose into T into dA. In this case it will be dx if you take tractive force to be per unit length. Okay, and this again I leave it up to you, you can carry out the integral. This will be equal to Q transpose into the tractive force on the element into the length of the element, okay, multiplied by 1/6, 1/6, 2/3. Okay, and this again we write that as Q transpose multiplied by, let's say, the tractive force vector for the element. This T and this T are different. Okay, this integral is just the same as the previous integral. You can try it out yourselves. Okay, so now if we look at the potential energy expression, I will rewrite the expression here, which is potential energy pi is equal to summation over all the elements of half of integral sigma transpose epsilon dV minus summation over all the elements of integral U transpose F dV minus summation over all the elements U transpose T dA minus sigma Qi Pi. Okay, this first term will now become summation over all the elements of half of Q transpose Ke into Q, okay, minus we have summation over all the elements of Q transpose multiplied by Fe minus summation over all the elements of Q transpose multiplied by TE minus sigma Qi Pi. Okay, now this expression is the same as the expression we had earlier. Okay, so this is equal to summation over all the elements of half Q transpose KEQ minus summation over all the elements of Q transpose multiplied by FE plus TE. FE plus TE will give us the element force vector, okay, and minus summation of Qi Pi. Okay, so this again I'll write that as summation over all the elements half of Q transpose KEQ minus summation over all the elements of Q transpose multiplied by the element body force vectors. Okay, the point loads can be taken incorporated into this. Okay, and then again the next step is also the same as what we had earlier. Okay, this summation of these matrix multiplications, we replace them by global matrices which will be of the type Q transpose K Q. Okay, minus become Q transpose F, where this F is a global force vector, vector. Okay, so this is again the expression for the total potential energy in the system. Okay, the method for assembling the stiffness matrix, the basic method will still remain the same. Okay, if we have, let's say, elements of this type, where let's say this is and so on. These numbers are the global node numbers. Okay, for each element, let's say this is my element number 1, this is element number 2, and this is my element number 3. Okay, we will say that element 1 is defined between nodes 1, 3 and 2. This is the first node, this is the second node, this is the third node. Okay, element 2 is defined between 3, 5 and 4. Okay, so this will be 3, this will be 5 and this will be 4. Okay, element 3 is defined between 5, 7 and 6. Okay, so my global stiffness matrix is going to have 7 locations in this case, where there are 7 nodes. Okay, so if I take all those 7 nodes, my first element is defined between nodes 1, 3 and 2. Okay, so first element will be defined between 1, 3 and 2 at these locations. Okay, my second element is defined between 3, 5 and 4. Okay, so second element will be defined between 3, 5 and 4. Okay, mind you, the sequence is important. Okay, I am writing this as 1, 3, 2 and not as 1, 2, 3. Because the second element, second node for this element E1 is node number 3. Okay, I can't interchange these numbers here. If I interchange them, all my forces etc. will go wrong. Okay. So element 2 is between 3, 5 and 4. So 3, 5 and 4. Okay, stiffness matrix for the first element will take these 9 locations, second element will take these 9 locations. Okay, and third is 5, 7 and 6. Okay, so this is, it will take 5, 7 and 6. So 5, 7 and 6 and so on. Okay, and the properties of the stiffness matrix are still retained. That means earlier we had said that a stiffness matrix for the two noded element was a symmetric matrix. Okay, this matrix is also symmetric. Okay, and if we do a numbering properly, we will still get a banded matrix. Okay, that means we have only diagonal elements and elements at a fixed distance from the diagonal. Okay, all other elements will be 0 and so on. Okay, but if my numbering is not correct, okay, that means in this case, let us say if I do my numbering like 1, 2, 3, 4, 5, 6 and 7, then my matrix will not remain a banded matrix. Okay, because the first element will be defined between 1, 2 and 5. Okay, so it will become 1, 2 and 5. This element will become non-zero. So it will not remain a banded matrix, but it will be a sparse matrix. Okay, so this global matrix will be either symmetric or it will be sparse.
So how does the local numbering 1, 3, 2 make a difference here?
This numbering? See, here in this table, what I am basically saying is that for each element, the local numbers 1, 2 and 3 correspond to global numbers 1, 3 and 2. The local number 1 for this node is global number 1, global node number 1.
So what difference will it make had the local node numbering been 1, 2, 3?
Had the local numbering been in a sequence? Okay, that means if I had taken my local numbering like this 1, 2 and 3, okay, what is eventually more important is this global numbering. Okay, but then my global numbering will not be straight like this, because okay, if I am doing the numbering like this, my node numbers will become this is my local number 1, this is my local number 2, this is my local number 3, this will become 2, this will become 3. My element 2 is defined between 3, 4 and 5. 3, 4 and 5. Element 3 will be defined between 5, 6 and 7. Okay, so in this case you will still get the same patterns. Okay, your matrix will still remain the same. Okay, but what happens is if you have see this quadratic element that we have taken, right now it is only for a one dimensional element. Later on we will see if we have a triangular element, even there we will take a 6 noded triangular element. Okay, there also we will do numbering like this.
So I'm asking, I don't see any advantage.
There is no specific advantage as far as there is no specific advantage that you will gain from this numbering. Okay, because eventually you can always change your global numbering to suit this particular pattern. Okay, but typically when an element is defined, Okay, you will find that eventually it basically comes down to the fact that it is by tradition. Okay, that you always define.
I think it's the other way around. V number 1, 2, 3, 4, 5, 6.
Again,
I think the number in a sequence 1, 2, 3, 4, 5, 6 in this element.
in this.
Yeah.
Anyway, this will come to when we come to two-dimensional elements. Okay, but in this, even if you number the elements 1, 2, 3 directly, okay, as far as your formulation is concerned, you won't lose anything. Okay, but typically you will always find the numbering to be 1, 2 and then 3. Possibly because you are extending it from linear elements. Possibly because of that reason. Okay, but as far as the technical numbering is concerned, it will probably not make a difference. Okay. Any other question on this particular thing? Okay. So the potential energy expression is given by this formula. Okay, now if you notice, the potential energy expression is the same as what we had earlier. A boundary condition is also going to be the same as what we had earlier. Okay, so our method of solving is also going to remain the same. Okay, eventually any type of element or any type of finite element formulation we choose, we'll try to get the same formulation and then use the same method that we have discussed already. Okay, whether it is two-dimensional elements or three-dimensional elements. Okay, our potential energy expression will be the same, the method of solving it will remain the same. The only thing that will change will be this matrix. That means the elements will have different number of nodes and a different numbering, different kind of local numbering and a global numbering. Okay, so the potential energy expression will always remain the same. What we will do from now onwards is that for different types of problems, for two-dimensional as well as three-dimensional problems, we will just see how to define elements, how to define shape functions, and how to get this potential energy expression. Okay, any questions on this?